So we're going to continue our talk about balanced and unbalanced forces by go ahead and completing our notes. And we've got a couple of I can statements here. The first is that you can explain the difference between a balanced and an unbalanced force. And we started to look at that a little bit yesterday. We'll also explain how forces interact with each other and how the interacting will affect the motion of an object, and will determine the net force acting on an object and what net force is. Yesterday, we kind of went over that a force is any push or pull that you're exerting on an object. Forces have a magnitude, which is how big they are, or the size of the force, and a direction, which way the force is being applied. Forces are measured in units called newtons, after Sir Isaac Newton. And forces usually occur in pairs. Let's first look at balanced forces. Yesterday, when we had our discussion, I heard the word equal and the word same and the word not moving. That all came up a lot. So, if we're to define forces, we're going to say forces are balanced when they are equal forces, but they're acting on an object in opposite directions. So, think of a tug of war match where both teams are going to pull with the same amount of force and nothing moves. So, if forces are balanced, there will not be any change in the object's motion. So, if the object is at rest, not moving, it will stay at rest. And if the object is in motion, moving at a constant speed, it will continue in motion. The net force is the combination of all of the forces that are acting on an object. So when you take all the forces going from the right, all the forces going from the left, all the forces pulling down and all the forces pushing up, all those forces combined is the net force. And when you have forces that are balanced, all of the forces will cancel each other out because they are equal and opposite, and your net force will be zero. Some examples, if you have a book or your Chromebook sitting on your desk, the forces acting on the book are balanced, and we know that because there's no change in the book's motion. The book is not moving, so the force of gravity pulling down on the book is equal to the force of the table that's pushing back up on that book. You probably never thought about the table applying a force, but the table is pushing back up on the book, and that's what keeps the book from falling all the way through the earth. The two girls are both pushing on the box. They're pushing in opposite directions, but with the same amount of force. Notice the arrows that are used to show force. So you have opposite arrows, but the same size. They cancel each other out, and we would say the forces acting on the box are balanced. And the same with the airplane and the boat. You've got all the forces equal and opposite, so there's no change in motion. The one thing that's kind of tricky to understand with balanced forces is that look at that airplane. If it's traveling at a constant speed through the air, it's not speeding up and it's not slowing down, we would say that the forces acting on the plane are balanced. It's not causing any change in motion. There's no speeding up, there's no slowing down. It stays balanced, even though it's going at a constant speed. We use something called force diagrams to show the forces that are acting on an object, and we use arrows to show the forces. So, yesterday I asked you to think of a way that you could use a symbol to depict a force, and the best way is to use an arrow. The size of the arrow represents the size of the force, and smaller forces have smaller arrows, while larger forces have bigger arrows. And the head of the arrow shows the direction that the force is being applied. Here you notice that the two forces are equal in strength or magnitude, but opposite in direction, and they'll cancel each other out, and your net force will be zero. So to calculate the net force for forces acting in opposite directions, you will subtract. That's the word you're going to put in the blank there. You will subtract the two forces. So 7 minus 7 gives you 0. Now let's look at unbalanced forces. When you have unbalanced forces, you have forces that are unequal and they're acting in opposite directions. Many of you yesterday said one force will be bigger than another. When you have one force that's greater than the other, it will cause a change in the motion of the object. So the object will change its motion when forces are unbalanced. Something's going to speed up, slow down, or change direction. Most of you understand speeding up and slowing down, but also changing direction. And the best way I can tell you to describe this is picture yourself in a car and you're going down the road at a constant speed. Oh, let's say you're traveling at 45 miles an hour. If the person driving the car accelerates and speeds up, you'll feel that change of motion. Your body will feel the car speed up. If the car slows down, you will feel that and you'll change motion. And if the person driving the car changes direction and turns the steering wheel, you'll also move inside the car. Whenever you feel that change in motion, you know the forces are unbalanced. If you stay at a constant 45 miles an hour, you're not speeding up and you're not slowing down and you're not changing direction, then your forces acting on you are balanced. And really, you don't feel like you're even moving. When you have unbalanced forces and one force is bigger than the other, the net force will always be greater than 0. So let's look at some examples. Here you have two students pushing the box in the same direction. When you have two students pushing in the same direction or two forces acting together, you'll want to add those forces and then subtract. So to calculate the net force for forces acting in the same direction, you'll add them together and then subtract from any forces going the opposite direction. Here they're not showing you forces going in the opposite direction, but notice that the boy pushing the box with the turquoise arrow added to the girl's push of the pink arrow together will give you that larger arrow at the bottom, the net force. We can also use force diagrams to show this. So here we have two forces, one is 7 newtons, the other 4. To calculate the net force for forces that are going opposite each other, we're going to subtract. So 7 minus 4 is going to give you 3 newtons. And you'll want to include the arrow showing which direction the net force is going to be moving. So here we have 3 newtons, and notice the arrow goes towards the right, and 3 newtons and the arrow goes towards the left. We can use force diagrams to also show the net force. So it's going to want to know what will the movement on this box look like. If you have 30 newtons going towards the right and 20 newtons going towards the left, the net force you will subtract and you should get 10 newtons to the right. So we'll use a force diagram here and show you the arrow. Notice that the 10 Newton arrow is smaller than both the 30 and the 20. It's what's left over from the two. If you could take the 20 arrow out of the 30, what you have left is a little 10 newtons that's left. And that's what we've depicted there. So let's say that the pug in the stroller is the 10 newtons of net force that you have left. It will move towards the right with 10 newtons of force. So let's try a problem. A man of a mass of 75 kilograms has a weight of 750 newtons. We're just talking about his weight as a force. And what we're doing there is looking at weight as a measure of the gravity acting on the man. So really, weight is the force of gravity here. This 750 newtons will act down on the table, and the table will exert a 750 Newton force upwards on the man. What will happen to the man? If you're thinking nothing, you're doing well because 750 newtons down and 750 newtons up will cancel each other out and you'll have a net force of 0. What would happen if the upward force were less than 750? So the table couldn't quite put the 750 newtons back. Then you would have a greater force of gravity going down than you would the table, and the man would fall through the table. So here we have 750 newtons down, and the table's 750 newtons up. They are equal and opposite, so we would say the forces are balanced, and there would be no change in motion. Let's look at this one. A child at a playground slides down a slide on a windless day. So there's no wind here. On your paper, describe 2 forces that affect the motion of the child as she moves down the slide. So you have to think about what forces might act on the child. The force of gravity is going to pull her down the slide. The slide is pushing back against her. We call that friction. Friction is that force that's resisting motion or slowing something down. The slide is also pushing back up on her so she doesn't fall through to the ground. Here we have a car going down a ramp, and we need to find which answer choice correctly shows the forces that are acting on the car. If we look at this first one, we have gravity pulling the car down towards the center of the earth, which looks pretty good. We have the ramp pushing up on the car, which is also going to work, and friction is going against the motion, slowing it down. This looks like a really good answer, but let's check the rest. If you look at B, gravity is pulling the car down, so that's pretty good. The ramp is pushing the car up, that's pretty good. Friction is going down the ramp, making it accelerate and go faster. That's where this one doesn't work. Friction always slows an object down and goes opposite of the motion of the object. If we go back up here to C, we have the ramp is pulling the car down. The ramp is pushing up, not down, so that doesn't work. Gravity is pulling the car up in the air. That doesn't work because gravity pulls down. But the friction arrow is correct. Friction does slow the car down. But because the ramp and gravity are incorrect, that makes C an incorrect answer. And if we look at D, friction will not push the car up in the air, and the ramp is not slowing the car down. So the best answer here would be A. Our last little bit, we're going to look at somebody that's skydiving, because when somebody's skydiving, you're going to have a lot of changes going from balanced to unbalanced, balanced to unbalanced. So we'll take a look at this one. Or maybe we won't. So that might be something that we go and look into when I'm back on Thursday. Now that you're done with the notes, you'll want to go ahead and use your notes to complete the defining force assignment that's in Polaris. You have multiple attempts, so after you complete your first attempt, view your assignment, see which ones you got right and which ones you didn't. You may work together after you do one attempt to see what you did wrong and discuss the answers to see if you can make a better second attempt. I'll see you back on Thursday.